In the previous lecture, we started our discussion on waves, and what I had told you about that waves are disturbances that travel from one place to the other, and particularly the waves that we are concentrating on were dispersionless. Waves, and that is, if I take a particular disturbance and let it travel down a string or somewhere, it does not change its shape as it travels along. And we obtained the form of the function. So, if this is a function f, then f x t for a wave, the disturbance is given as a function of either x minus v t or f some other function f, let us call it f bar t minus x over v. This would be for the waves traveling to the right. So, waves traveling, in the informal language I am calling it to the right, but actually waves traveling in the positive x direction, and for the waves traveling in the negative x direction, for the waves traveling in the negative x direction, this function of x t would be given as some function of x plus v t or some other function of t plus x over v. So, these are traveling waves, right. Now, it may so happen that at certain place, if there is a wave traveling one way and there is another wave which is coming the other way, or I create a disturbance and it meets another disturbance somewhere else. So, with that, suppose there is a disturbance which is sinusoidal. So, this disturbance is traveling and so is the sinusoidal disturbance traveling. How does the final displacement look? So, the question we are asking is as follows: what happens when two or more waves arrive at a place at the same time? Let me explain what we mean by what happens. So, what we are asking is, what is the displacement as we saw in the string, or pressure as we saw in pressure waves or sound waves, when two different waves arrive at a place at the same time. So, this is what we want to answer, and this is answered by the superposition of waves. What the superposition says, so we are talking about superposition. What the superposition says is that if there are two or more waves arriving at a point at the same time. That means there is a wave f1 arriving, there is a wave f2 arriving, and so on. Then the net displacement or pressure, these are the two waves that we have studied earlier, at that point is given by the sum of individual displacements or pressures. I will keep using word displacement, I do not want to write pressure again and again. So, the net displacement at that point f x t will be equal to f 1 x t plus f 2 x t and so on. So, at any point when I see the net displacement, it will be sum of all these different waves arriving there. Now, this is very particular to waves satisfying linear differential equation. I am stating this, that this arises out of waves satisfying linear differential equation for completeness. The waves that we are considering right now are essentially those that satisfy linear differential equation. So, you can take it for granted that we are going to use superposition principle to describe what happens when two or more waves arrive at a point. So, principle of superposition gives me the net displacement, and the principle of superposition says that the net displacement at that point is going to be the sum of individual displacements or individual pressures. For example, when I am speaking and somebody else also is speaking, at a certain point the pressure difference is going to be sum of these two pressure differences. If I have a string going and two persons create two different waves on it, at any point the displacement of the string is going to be given by the sum of the displacements created by the waves by these two persons. So, let me just briefly restate what I just said, is that there is something called the principle of superposition, and I will just state it mathematically now, that the net displacement at a point is going to be sum of individual displacements given by individual waves at that point. And now I am going to specialize to sinusoidal waves, and let me remind you what these are. In these waves, the displacement is given as some amplitude sine of k x minus omega t. I could equally well write this as amplitude sine of omega t minus k x, or some amplitude cosine k x minus omega t, and any other form for the waves travelling towards the positive x direction, or sine of k x plus omega t for waves travelling to the negative x direction. So, let me indicate that by these arrows, and let me remind you that k is omega over v, k is also same as 2 pi over lambda. The speed of waves is given by the frequency times lambda, and all these things we have done earlier. So, what principle of superposition now says then, that at any point the net displacement due to different sinusoidal waves arriving is going to be amplitude 1 sine of k x minus omega t. In fact, let me make it k 1 and omega 1 t plus a 2 sine of k 2 x minus omega 2 t plus a 3 sine of, it could be k 3 x, the wave could be traveling towards the negative x direction omega 3 t, right. It could be of some other form, b 1 cosine of k 4 x plus omega 4 t and so on. So, all these possibilities exist. That net displacement is going to be a sum of all these. The consequence of superposition principle is that during reflection something happens, right, and I am going to discuss that. Standing waves are formed by two waves traveling in the opposite direction, that is also we are going to discuss. So, all these phenomena in the later lectures I am going to discuss about beats and interference, that all these phenomena are basically consequence of superposition principle. So, let us take them one by one. So, let me just write them first. The consequences of superposition principle, right. So, we are going to see reflection at a boundary, then we are going to see standing waves, and later in your 12th grade you are going to study interference of waves. Part of it we are going to do here called the beat phenomena. So, let us take them one by one. Number 1, reflection of waves at a boundary. In describing all these phenomena mathematically, I am going to choose my points conveniently so that mathematics becomes simple. So, in this case what I am going to do is, let there be a wave which is coming to the right and gets reflected at point x equals 0 by a hard wall, all right. It could be a string tied on a wall, or it could be a pipe which is open at this end, so that delta p will be 0 out here. It can sustain, open and cannot sustain any pressure difference. So, the pressure out here is going to be the same as the atmospheric pressure, and that gives you delta p equal to 0. So, these are two things which are the same. That means, a string tied at a hard wall and an open ended pipe where the pressure difference would not be sustained. In this case, suppose there is a wave coming in. So, let me show it, although I am going to finally consider a sine wave, let me show a displacement coming in. It comes in and at any boundary this reflects. So, this is going to reflect here. So, it gets reflected either in the same form or in the negative direction. It will in fact be in the negative direction, as I am going to show now. Now, at any given time, the displacement at this point where the string is tied, so displacement at the point where the string is tied is going to be 0, and we will use that to show that during reflection the pulse actually changes sign. So, let us do that now. So, I am considering now reflection of a wave on a string at the point where the string is tied. Okay, so the phenomena we are considering is, here is a string and it is tied at a certain point and there is a wave that comes in. So, at the boundary, at x equals 0, I have conveniently chosen this point to be x equals 0, we are going to have net displacement equal to 0. And net displacement I know is equal to sum of individual displacements. In particular here, this is going to be the displacement due to incoming wave plus displacement due to the reflected wave, and I know the left hand side is 0. So, what I have is that 0 is equal to displacement due to incoming wave plus displacement due to the reflected wave. And this is at a hard boundary where there can be no displacement, and this immediately tells you that displacement of the reflected wave is equal to minus, and that is opposite to the displacement due to the incoming wave. So, they are always opposite. So, what will happen is that this wave comes in. Let me show the incoming wave by red. It comes in, it is coming in towards the wall, and when it gets reflected, it is going to change the displacement direction. So, reflected wave is going to be in the opposite direction. In particular now, let us take a sine wave. That means, I am looking at this string on which a sine wave is coming in. So, this is the wave coming in, and simultaneously when it hits the wall, it gets reflected. How are the two displacements related? So, incoming wave now the displacement, let me write this as y, x t is going to be given by some amplitude a sine of k x minus omega t. So, this is incoming, and let me write y reflected x t as b sine, frequency cannot change, k cannot change, lambda cannot change. So, because the same medium, but it is going to be sine k x plus omega t. We are looking at x equals 0, and therefore, y net at x equals 0 is nothing but a minus a sine of omega t plus b sine of omega t, and this should be 0. What does this tell me? This tells me that b equals a. So, what do we have? We have incoming wave is equal to A sine k x minus omega t, and reflected wave equals A sine k x plus omega t. Notice that I can write reflected wave at x equals 0 as A sine of omega t, which is equal to minus of minus A sine of omega t, which is minus of y incoming. So, the two waves are actually opposite, the displacements are opposite to each other. So, I can write that y reflected is equal to A sine of omega t, which I can also write as A sine of minus omega t plus pi. Why? Because A sine of minus omega t plus pi is going to be minus of A sine of minus omega t, which is equal to A sine of omega t. But the purpose of writing it in this form is as follows, that y reflected is equal to A sine of minus omega t plus pi. This minus omega t actually shows the phase of the incoming wave. So, we have to add a phase of pi to show the displacement of reflected wave. So, let me write that. To get the reflected wave, we add a phase of pi to the phase of incoming wave, and this is only for when the reflection is from a hard wall. So, there is a phase difference, right? There is a phase difference, implies that there is a phase difference of pi between phases of incoming and reflected waves when the reflection is from a hard wall. Let us see this pictorially. So, what is happening is, here is the wall, and at any given time, let us say the incoming wave is like this. At this time, the reflected wave, so this is incoming wave is sine of k x minus omega t at some given time t. The reflected wave is opposite. So, the red one, this is reflected wave, which is sine of k x plus omega t at that same time. So, what is happening is, when a little time later, when the incoming wave has moved forward, so let us say this has become like this, it has moved forward, so that this maximum has advanced by some amount. At the same time, the wave which is coming due to reflection would also move forward, but in the other direction. So, this would have done like this. So that these two displacements remain exactly opposite. You see, whatever is the displacement here, same displacement is here. So, when this fellow moves this way and this fellow moves this way, the displacement at x equals 0 remains 0, and this is how the net displacement is maintained to be 0 at point x equals 0. So, this is about the reflection. Now, this has consequences. This has consequences that reflection at boundaries creates reflected waves, and what we have seen just now is the displacement at only the point where the reflection is taking place. What we want to know is what happens to the displacement at other points, and what we will see is this gives rise to the superposition of incoming and reflected waves gives rise to standing waves. What do I mean by standing waves? These are the waves that are not traveling, they are standing right there. But before we do that, I will just like to leave you with a question about reflection. I have talked about reflection at a boundary where the pressure difference or the displacement is 0. I would like you to think about what would happen at a point where the displacement is not 0. For example, I could have a string here tied to a ring and tie another string on this side. In that case, a wave which is coming in would make this ring also go up and down, and therefore, it will create a wave here also and a wave which is reflected. In this case, what will be the displacement here and what would be the ratio of the waves which are reflected, the amplitude of the reflected wave, what will be the amplitude of the transmitted wave. This is something which you will learn in advanced classes, but for the time being qualitatively you should think about what all could happen at the boundary where this ring is there, right. So, what I am talking about is the net displacement at the boundary is not equal to 0. In terms of pressure waves, what it means is that the delta P, the pressure difference at the boundary is not equal to 0. That would happen, for example, if I have a pipe and there is a hard wall on one side. Here, no matter what the pressure difference is, nothing really happens. So, delta P here need not be 0. On the other hand, on the side where the pipe is open, delta P is 0. So, I will let you think about this, and now we will move on to discuss standing waves. So, to understand the standing waves, let us consider a wave moving in the positive x direction, and this would be amplitude times sine kx minus omega t, and superpose this with a wave of the same amplitude. So, a sine kx plus omega t traveling in the negative x direction. So, what we have is we have a wave which is traveling to the right, and I am superposing this with another wave which is traveling to the left. And let us see what is the net result. Keep in mind that the amplitudes of the two waves are the same. So, the net result y x t at any given point is going to be a sine of k x minus omega t plus a sine of k x plus omega t, and I can expand this and write this as a sine k x cosine of omega t minus a cosine of k x sine of omega t plus a sine k x cosine of omega t plus a cosine of k x sine of omega t. And if I add these, I get y x t, which is of the form 2a sine k x cosine of omega t, because the second term cancels. Now, this is not of the form, this is not of the form f of either x minus v t or f of x plus v t. So, x and t are not coming in this form in the combination of x minus v t or x plus v t or t minus x over v or t plus x over v, but they are separated. So, what does it represent? This represents not a traveling wave, but it represents a standing wave. So, you understand what we mean by standing waves. It is a wave which is superposition of two waves of equal amplitude going in opposite directions, so that the net result is that nothing is traveling, because if it traveled, it would have had the form of a function of x minus v t or x plus v t or t plus x over v or t minus x over v. It does not have that form. Nonetheless, there is a displacement which is a function of time and x, and therefore, we call it a standing wave. Let us make a picture of it and see what it means. So, I have the form y x t equals 2a sine of k x cosine of omega t. Let me call this 2a, just another constant b, sine of k x cosine of omega t. So, if I look at it, what it is that the displacement at any given time is a function of x. So, the displacement is like this. At any given time, it could go to the left and to the right. So, this is b sine of k x. As time changes, each point performs a simple harmonic motion with frequency omega, and time dependence is given as cosine of omega t. So, this point, for example, the one shown by red arrow, will go up and down with frequency omega. The point next to it, shown by green, would go up and down with frequency, same frequency omega. This will also have a time dependence of cosine omega t. So, with time, what you will see is this. Suppose I were to just focus on this segment in the middle, what you are going to see is that this whole thing is just oscillating back and forth. Compare this with a traveling wave, where what you would have seen with time is given a displacement like this, as time progressed, this would have shifted. This would have shifted by v delta t in time delta t. That is not happening in the wave shown above this, right. This maximum point is not shifting. All that is happening is oscillating back and forth right at that position. It is as if there are many simple harmonic oscillators at each point, each oscillating with different amplitude, but they are all related with each other, so that the amplitudes change at as sine of k x. So, this is known as the standing wave. And it is a superposition of two waves traveling in opposite direction. So, it is as if each point is oscillating with this amplitude given by b sine of k x. So, what you will see in books is that when they show a standing wave, it is usually shown like this, and you also see a picture like this. What it means is that this is showing the net displacement as a function of time. Each point is going back and forth with the frequency omega. So, this is representing the displacement y x t equals some amplitude b sine of k x cosine of omega t. We could also have taken other forms, sinusoidal though, and could have written them as some constant c cosine of k x cosine of omega t, or some other constant d sine of k x sine of omega t. All depends on what phase are we choosing at time t equals 0, what displacement we are choosing, but this is how it looks. Notice that while oscillating, there is going to be a time when this entire string is going to be flat, but all the points would be moving down or moving up at that point. So, this is just oscillating back and forth, and that is a standing wave. Now, what we will consider are different examples of standing waves. In all this, unless required by certain displacements, I am going to assume that my displacement y x t is going to be of the form a or b. Let me write a again, a sine of k x cosine of omega t. I might take, depending on where I choose my x, some other form according to my own convenience, but that does not matter. So, I could also choose, for example, a cosine of k x sine of omega t, or some other combination, but this is the general form. So, let us take the first example as standing wave. On a string. What I mean by that is, I have a string which is tied at one end. I could either tie it at the other end and there is some tension in it, or I could also have this string tied at one end and the other end is being moved up and down. So, let us say this point is x equals 0. So, what would happen is, when I create a wave in this, suppose I create a pulse, it is going to move this way and then move back. Net displacement is going to be given by sum of these two, reflected and incoming pulse. At x equals 0, the net displacement is always 0. In particular, if I now specialize to sinusoidal waves, in the string tied at both ends, there is going to be a sinusoidal wave incoming and outgoing, and the superposition is going to give me a standing wave, and net displacement at both points is going to be 0. So, as I said earlier, standing waves are generally shown like this, and what is happening in this case is, each point is going to be oscillating back and forth at this amplitude given by sin k x. And so on. On the other hand, if I have this string tied at one end and vibrating on the other side, I would have a 0 net displacement at this point and the largest possible displacement at the open end. This is going to be moving up and down, and all these points are then going to be moving up and down by the same amplitude. So, these are two different kinds of standing waves, one with the string tied at both ends and the other with the string tied at one end and free to move at the other end. I am taking these points to be at x equals 0. So, let us analyze these mathematically and then also see what does it mean physically. So, mathematically I will take first the case of string tied at both ends. In this case, as I said earlier, the displacement y x t is going to be given by a sin k x cosine of omega t. I am taking the left hand end of this string to be at x equals 0 and the right hand to be x equals L. That means the length of the string is equal to L. So, when I take this displacement y x t equals a sin k x cosine of omega t at x equals 0, y is 0, which should be the case because that is what I want. Now, we also have that y at x equals L at any time should also be 0. Why? Because this string is tied at that point, and therefore, I should have a sin of k x cosine of omega t at L, which is equal to a sin of k L cosine of omega t equals 0 for the string tied at both ends. So, what we have is that for this string which is tied at both ends, I have y x t equals a sin k x cosine of omega t, and I have a sin k L cosine of omega t equals 0. Now, cosine of omega t varies with time, so it cannot be 0. A is the amplitude. So, the only term that can make it 0 is that sin k L must be 0, and this implies that k L is equal to some integer n times pi. And therefore, in this case I am going to have k L equals n pi or k equals n pi over L. Now, k we have said earlier is omega over the speed of waves, and this should be equal to n pi over L. So, omega is 2 pi times the frequency of oscillation, and therefore, I have 2 pi frequency of oscillation over V is equal to n pi over L. Pi cancels from both sides, and the frequencies that I get then nu is going to be equal to n times V over 2L. So, notice that all frequencies are not allowed. The string can vibrate only at certain frequencies, and I am going to call them nu n, and they are going to be multiples of V over 2L. So, nu n we have found to be equal to n V over 2L, and V in this case happens to be square root of tension over mass per unit length. So, the frequencies at which the string can vibrate is n over 2 L square root of T over mu. This is based on the fact that sin k L is equal to 0 and therefore, k is equal to 2 pi over lambda is equal to n pi or lambda times L. Lambda is equal to 2 L over n. Let us understand this physically. What it means is that for this string tied between two ends, since the end points are at 0 displacement, the only way that could happen for a given frequency is either the wave is like this, or it makes 2 loops, or it makes 3 loops, and each of this half loop is nothing but lambda by 2. So, what I should have is that lambda by 2 times n, where n is an integer, n could be 1, 2 or 3, should be equal to L, which implies that lambda is equal to 2 L over n. So, we have seen mathematically now that to keep the two ends the same, k should be of the form k equals n pi, and physically what it means is that I could have only integer number of half wavelengths through this length, and that determines the frequency of this string. So, it cannot vibrate at any other frequency but certain frequencies. Now, these points which are always at 0 displacements are known as the nodes. So, for this string which is vibrating at certain frequency with both ends tied, let me make a general standing wave like this. The points which are always at 0 displacement, these ones which I am putting these big dots at, are known as nodes. The points which are at maximum displacement, maximum amplitude, are known as antinodes. Distance between nodes is equal to lambda by 2. Distance between two antinodes, that means adjacent antinodes, is also lambda by 2, and we have seen that the frequency at which it vibrates is going to be n over 2 L square root of T over mu. The other example I am going to now take is, suppose I take the same string, tie it at one side, and on the other side I attach it with a vibrating, could be oscillator, I could be vibrating with my hand, and in that case the standing wave, which is of the form A sin k x cosine omega t y x t, y at 0 would still be 0, but what I want to have now is that y at x equals L and t, which is A sin k L cosine of omega t, would have maximum displacement at x equals L, and that means k L should be 2 n plus 1 times pi by 2, and k being 2 pi over lambda should be equal to 2 n plus 1 pi over 2 L. I cancel pi on both sides and get lambda equals 4 L over 2 n plus 1. In this case, lambda is slightly different, and the frequencies nu n, which is V over lambda, I am doing derivation slightly differently this time just to give you different ideas, is equal to 4 L divided by 2n plus 1, which is going to be V over 4L times 2n plus 1. So, this time the nature is slightly different, and I could again write this as n plus a half V over 2L. So, in this case the frequencies are slightly different because one end is open and one is not. And again I have a physical interpretation that in this case the waves are going to be of the form where the open end has maximum displacement. So, I am going to have lambda by 2 the n segment is going to be of the length lambda by 4. So, what I am going to have is lambda by 4 times 2n plus 1 is going to be equal to L, and that immediately gives me lambda equals 4L over 2n plus 1. So, that is the physical interpretation. Mathematically we could just write what KL should be and get our answer. So, I will conclude this lecture now by summarizing what we have done. In the next lecture I am going to consider open pipes and organ pipes and the oscillation of air columns in them and beats and Doppler phenomena. So, let me conclude this lecture by summarizing what all we have learnt. We learnt about principle of superposition that said that displacement at any point is the sum of displacements due to individual waves arriving there. Then we learnt about reflection of a wave from a boundary. In particular, we learned that there is a phase difference of pi between the phases of incoming and reflected waves when the boundary is hard, that means no displacement at the boundary. And finally, we learnt about standing waves that are like simple harmonic oscillators with different amplitude oscillating at each point all with the same frequency, and we learnt about standing waves on a string and obtain the frequencies at which the string can vibrate both mathematically and looked at it physically also. What does it mean?